All right, this is podcast 4.1 for chemistry. We're going to talk about the VSEPR theory, and we'll get to that in just a minute about what that means. And we're also going to talk about drawing Lewis dot diagrams and Lewis structures for molecules. So if we remember Lewis dot diagrams, they were where we had the symbol in the middle and then we would put the dots around it depending on how many valence electrons it has. Remember that we're talking only the valence electrons, so the very outer electrons are the ones we're going to focus on because these are the ones that participate in bonding. So the valence electrons are the ones that participate in bonding. And we can figure out the number of valence electrons that an element has by looking at the column that it's in on the periodic table. So if it's in 1A, it has 1 valence electron. If it's in 2A, it has 2. 3A would have 3. 5A would have 5. So you just use that column heading to tell you how many valence electrons it has. And we can draw those Lewis dot diagrams if we want to review that really quick so you can see what they look like. So column 1A we said had 1 valence electron, and there's where you can see all the symbols and they all just have 1 dot after them. 2A they have 2 dots, 3A they have 3, and on and on. Remembering that the only exception to this rule is hydrogen, which only has 2 dots even though it's in the 8A column. We need to be able to figure out the number of valence electrons these elements have pretty quickly because we're going to use that when we draw Lewis structures for our covalent compounds. We're going to touch really fast on ionic bonds though. So ionic bonds, if we remember, are when electrons are transferred. So we have a give and take of electrons. And the metal always gives to the nonmetal. So that's why your metals always form their positive charge and the nonmetals form the negative charge, because these are always losing their electrons to the nonmetals, which are picking them up. So our example that they're showing us in this picture is the formation of sodium chloride, NaCl. We look at Na, sodium, which is in column 1A, so it has 1 valence electron. Chlorine is in 7A, so it has 7 valence electrons. It needs to have 8 because everybody wants to have a full octet. They want to have a full outer shell. So sodium is going to lose 1 in order to have a full outer shell, because once its outer shell is empty, then the next one down is full, and that makes it stable. So it's going to give that 1 valence electron away to chlorine. Chlorine then will pick up a full outer shell because it will now have 8. So since sodium gave away one of its electrons, it forms the positive, chlorine would form the negative. And that attraction between the positive and the negative charges that you have here, that force is what the ionic bond is. So the ionic bond is the force between these two oppositely charged particles. But that's as far as we're really going to go with ionic bonds. The rest of this time we're going to spend drawing Lewis structures with covalent compounds. So covalent compounds are when we share electrons. And when we're sharing electrons, we draw structures to show that, and we use lines. Lines show us that there are electrons being shared. So in this example, we have water. We have the 2 hydrogens bonding with the oxygen, and oxygen has 6 valence electrons, each hydrogen has 1. So what they end up doing is they end up sharing. The hydrogen shares with that, and the hydrogen shares right there. So oxygen has a full outer shell, because it has 8, and hydrogen is happy because it has 2. Remember, hydrogen wants to be like helium, so it really only needs 2 electrons to be stable. But in order to represent these electrons right here that are being shared, we do a single line. So this line right here is showing shared electrons, and it's showing 2 shared electrons. So each of these are showing 2 shared electrons between the hydrogen and the oxygen. They can go both ways. So when we want to know what shape these things are going to look like, how do I know that water is going to look like Mickey Mouse with the hydrogens kind of sitting up higher? Why are the hydrogens not sitting at 180 degrees from each other? We use what's called the VSEPR theory. You can't just look at the formula to know. So for example, if I just looked at H2O, maybe I would think it's just H and then O and then H, and this would be 180 degrees between those 2 hydrogens, when in fact it's a hydrogen and oxygen, and then the hydrogen goes back up, and it's much less than 180. So another example is SO2. These would not look the same if you were to draw them. Let's do carbon dioxide actually looks like this. There is 180 degrees between them. And then the sulfur dioxide looks like this. So they're bent down at an angle, and we want to know, how can you predict what these molecules are going to look like when they go together? So this VSEPR theory stands for valence shell electron pair repulsion. And that's a lot of words, so the VSEPR theory. What it says is that electrons are going to position themselves as far away from each other as possible. So remember, electrons are negative and they're going to repel each other, and they're going to get as far away from each other as they can. This is the system that we use to predict molecular shapes, and it's based on that idea that electrons are going to get as far away from each other as possible. That's going to minimize the repulsion of the shared and unshared pairs of electrons around the central atom. So it's all about the electrons minimizing the repulsions between them. We want to get them as far away from each other as we can. So when we're drawing these molecules, there's a lot of steps, and these are written on your handout so you don't have to rewrite them. And it kind of looks complicated, but it goes pretty quickly. The first thing you want to do when you're going to draw a molecule is count the number of electrons available to bond. That's where you just add up the valence electrons, so you're going to use the column heading. And you're going to make sure you account for multiple atoms of each type. So for example, if I were doing H2O, each hydrogen would have 1, so it'd be 2 times 1 because I have 2 hydrogens each with 1 valence electron, and then my oxygen would have 6. So that would have a total of 8 valence electrons I can use in order to draw this structure. You want to identify the central atom. Usually it's the first element that is the central atom. There is the exception here. Hydrogen can never be. Hydrogen is never the central atom. Is never the central atom. And then if all else fails, you can also look for the atom with the lowest electronegativity. That'll cue you in on who goes in the middle. You're going to place a single bond, which remember we said was a single line between the central atom and the terminal atoms. Terminal just means the atoms that are outside the central atom. They're on the ends. Then you're going to give each atom a full octet. The exception to that is hydrogen, because hydrogen just wants a single line. It just wants 2 electrons with dots. So we'll go through an example where you can see all this. And then you have to count and rearrange your structure so that it matches what we added up to in number 1. So a lot of rules, but it's almost easier if we just kind of go through some examples. So practice problem set number 1. The first one they gave us is phosphorus trihydride. What you're going to do is you're going to look for phosphorus, and phosphorus has 5 valence electrons because it's in column 5A, plus I have 3 hydrogens, and each hydrogen has 1 valence electron. So if I add all those up, I have 8 electrons. So that tells me my final structure can only have 8 electrons showing. Phosphorus comes first, and I know hydrogen can't ever go in the middle, so I'm going to put phosphorus in the middle, and I'm going to connect each hydrogen with a single bond. And then I have to give everybody a full octet. Well, hydrogen is happy with just a single bond. It never gets dots. So this is what hydrogen will look like. It's stable. Phosphorus, however, needs to have 8 because an octet means 8. Right now it has 2, 4, 6. So what I do is I give it a lone pair of electrons on top there. That's the 8 electrons. So now phosphorus is surrounded by 8 electrons. Each hydrogen has 2 electrons. And this structure is showing 2, 4, 6, 8 electrons, which matches what I said I could use. So this would be the correct structure for that molecule. Moving to this one. I have 2 hydrogens, each with 1 valence electron, plus my sulfur, which is in 6A, so it has 6 valence electrons. So my total again is going to be 8. I know hydrogen can't go in the middle, so I'm going to put sulfur there. And then I'm just going to attach a hydrogen on either side. At this point it doesn't matter, you just kind of want to probably position these things as far away from each other as you can. So you have your H and your H. Okay, hydrogens are happy, but my sulfur still needs to have 8 around it. So this is 2, 4, I need to give it a lone pair on the top and a lone pair of electrons on the bottom. So this would be 2, 4, 6, 8 electrons. Everyone is stable, they have what they need. That also matches here, so I don't have to do any rearranging. That would be the correct structure for that molecule. Going to the next one, hydrochloric acid. Hydrogen has 1 valence electron, chlorine has 7, so again I'm getting 8 valence electrons is what I can use. There is no central atom, they're just hooked to each other because there's only 2 of them, so it's just H connected to a Cl. Hydrogen is happy, it has its 1 bond going to it, so it has its 2 electrons. Chlorine though needs more, so I would draw in 3 sets of lone electron pairs because now chlorine is surrounded by 2, 4, 6, 8 electrons, and now it has a full octet, so it's happy. The structure also has only 8 electrons showing, which makes it match up with what I have here, so I don't have to do any rearranging. That would be the structure for hydrochloric acid. For this one, carbon tetrachloride, carbon is in 4A, so it had 4. Plus, I have chlorines, and there's 4 of them, and each chlorine has 7 valence electrons. If I were to add all that up, that's 28 plus 4 would be 32 electrons. So this one has a significant amount more than what we've been doing. So carbon's going to go in the middle, and a lot of times carbon is the central atom, so you can go ahead and put it there. I'm going to start by attaching 4 chlorines around the carbon. Okay. Carbon is happy because it has 2, 4, 6, 8 electrons around it, so I don't have to do anything else to the carbon. The chlorines, however, each only have 2 electrons. So around each chlorine, I'm going to have to add 3 sets of lone electron pairs. So once I'm finished here and I give everybody 8, I can go back and count. So I know each set here has 8. So there's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. It matches there. Everybody has 8, so that would be the structure I would use for carbon tetrachloride. Moving on to our problem set 2. This is where we're going to have to start rearranging our electrons. We're going to have to form double and triple bonds. So we have nitrogen trifluoride. Nitrogen has 3 valence electrons. No, it doesn't. It has 5. And then fluorines, there are 3 of them and they have 7. So 3 times 7, 21 plus 5 is 26. So my structure can have 26. Nitrogen comes first, it does go in the middle. So I'm going to attach 3 fluorines. It does not matter where you could point one fluorine up instead of how I pointed it down. At this point it does not matter. Okay, nitrogen has 2, 4, 6 electrons around it. It needs to have 1 more lone pair on top there to have 8. Then I have to go to each of my fluorines and make sure that they have 8. So I'm going to draw 3 sets of lone electron pairs around my fluorines. And then if I go back, everybody has 8, so I count them up. 2, 4, 6, 8, 16, 24, plus another 2 would be 26. So that would be the correct structure for nitrogen trifluoride. Okay, this one we have carbon disulfide. Carbon is in 4A, it has 4 valence electrons. There are 2 sulfurs, each with 6 valence electrons. So that's going to give me 12 plus 4 is 16 electrons that I can use for my structure. Okay, carbon goes in the middle. I'm going to put 1 sulfur off to each side. And I'm going to start by giving everybody 8. So carbon needed 2 lone pairs, so 2, 4, 6, 8 around the carbon. And each sulfur needs 8 valence electrons. Okay, so here's my starting point. If I count up my total number of electrons, I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 20 is too much. So if we look back on our notes, what we said is if we have too much, we have to create double or triple bonds. We need to make more electrons shared. They can't have so many lone electrons on their own. So when you make a double bond, what you're going to do, you can pick either side, it does not matter. You're going to draw another line here and it looks like an equal sign. When I do that though, that's showing that instead of just 2 electrons being shared between these, there's now 4. So that means I have to get rid of a pair of lone electrons off the 2 atoms that I just connected, because that's going to keep everybody at 8. If I look at this sulfur, it has 2, 4, 6, 8 electrons still around it. If I look at the carbon, it still has 2, 4, 6, 8 electrons around it. So make sure if you create a double or a triple bond that you get rid of a pair of lone electrons off of each of the atoms that you connected. If I recount that up, I'm going to end up with 18 electrons, which is still too many. And what you want to do is you want to create a double bond on the other side, because we kind of want things to stay symmetrical. You don't want to have a triple bond on one side and a double bond on the other. So I'm going to go ahead and create another double bond on this side, and I'm going to get rid of a lone pair on the sulfur and a lone pair on the carbon. So my final structure is going to be a sulfur with 2 lone electron pairs, double bonded to a carbon, which is double bonded to another sulfur with its 2 lone electron pairs. So that's how it looks kind of more neatly drawn without all the scribble marks of the lone electron pairs being scribbled out. So this would be the correct structure. It has 16 electrons showing to match what we counted up that we had available for bonding. Okay, last two. This is the perchlorate ion, and how you deal with ions is you have to remember what that actually means. If you have a negative charge, it actually means that you gained electrons. So if I'm doing that, I'm going to add to my total. So for example, chlorine has 7 valence electrons. I have 4 oxygens. Each oxygen has 6 valence electrons. And because this is a -1 charge, I'm going to add 1 more to my total. And what you're going to do then is if you add all those up, you're going to end up with 32 electrons. So I'm going to put chlorine in the middle, and then I'm going to start with my 4 O's around the outside. And then chlorine is happy, it has 8. And I'm going to give all the oxygens really sloppy lone pairs. And the last one here. And then if I add all these up to check, because I need to make sure it adds up to 32, there's 8 in each of these little arms sticking out. So 8 times 4 would be 32, and that's what my answer is. I do need to show, however, that this molecule has an overall charge. So you just put square brackets around the structure that you drew, and you put the charge on the outside of it. That just shows that this thing has a charge of -1. All right, lastly, we have carbon monoxide. Carbon has 5 valence electrons. No, it doesn't. It only has 4. Oxygen has 6, so that gives me a total of 10. You should never come out with an odd number of valence electrons. If you did something wrong, and that's a good time to go back and check and see what you did. Okay, again, no central atom. They're just connected. I'm going to start by giving everybody 8. If I add these up, I have 2, 4, 6, 8, 10, 12, 14, which is way too much. So I'm going to do a double bond. And I get rid of a lone pair off each of the atoms I connected. So now I have 2, 4, 6, 8, 10, 12, which is still too many. Triple bond. Get rid of another lone pair off of each carbon and each oxygen. So this is 2, 4, 6, 8, 10 electrons. Everybody still has 8 because remember they're sharing the 6 in the middle here. They each have 1 lone pair. So this is the correct structure. If we cleaned that up a little bit, it would look like this. So there's your structure for carbon monoxide. Okay, that is the end of the podcast. You need to make sure that you can count the number of valence electrons that are in these molecules pretty quickly and accurately. And then don't forget about the charged molecules, the anions and the cations. Make sure you know what to do with those, whether you add or subtract electrons.